So this last video we're going to explore what a real gas is and how it differs from ideal gases. So finally we're going to talk about the difference between real gases and ideal gases, and I can guarantee you there will be questions about this on the AP exam. This is an important concept, sorry. So first we need to realize that no gas is an ideal gas. Okay? Because remember, if you look back at your notes at the 5 precepts of kinetic molecular theory, we said that in kinetic molecular theory there were no intermolecular forces between the molecules, and that is not true. There are some intermolecular forces between gas molecules, but for purposes of writing our gas laws, many times we don't need to pay attention to these because they're weak. So that's why we can say this usually, and it's usually true because the intermolecular forces are usually so weak that they don't make a difference. Another point in our kinetic molecular theory was that the molecules do not have any volume. Now how can that be? How can you have something that has no volume? All atoms have volume. They're there. They're not there. They're there. So this in truth is not really true. However, the reason we can say it and use equations that assume that is because many times with the way we're working with our gases, the volume is so small it does not make a difference. So the volume does not make a difference. So when our intermolecular forces are so weak that they don't make a difference, they're not really affecting how the gas is behaving, and when the volume of our molecules and atoms is so tiny compared to the overall volume of the gas, then that doesn't make a difference. That's when we can use the ideal gas law and Boyle's law and Charles's law, because they're so weak they don't make a difference. If we were to have a situation where the intermolecular forces do make a difference, or the volume does make a difference, then we have to use more complex equations. And those equations are, one of them is called van der Waals equation, and I'll write it for you. So here we have van der Waals equation, and you can see it's somewhat similar to the ideal gas law because on the right side you have nRT, which is what you have here. But you don't just have pressure and volume on the left side. Pressure has been adjusted. This term here where A is a constant and N is the number of moles, and this adjustment takes into account the intermolecular forces. Over here we're adjusting volume to take into account the fact that molecules and atoms actually do have some volume. Using this equation is a pain in the neck, and we're not going to use it mathematically in this class, but we need to describe when we would have to use it, and so that's what we're going to talk about right now. So what we're thinking about is when the intermolecular forces between our molecules would be so strong that we could not use the ideal gas law, okay? And we're also thinking about when would the volume of the molecules be so significant compared to the volume of the container that we could not use the ideal gas law. So let's think about intermolecular forces first. So we're going to have a container and it's going to be filled with gas molecules and they're zipping around and moving around. If this container is at a very high temperature, or relatively high temperature, then all these molecules have a lot of kinetic energy and they're moving around rapidly. So if they have a lot of kinetic energy, they have a lot of speed, they're moving really quickly. So there's no time, if they're moving really quickly, for intermolecular forces to cause one to be attracted to another because they're moving so fast. The intermolecular forces can't make a difference because by the time this one starts to get attracted to this one, he's already moved all the way over there. So at high temperatures, gases behave like ideal gases. And you can... So what does that mean? That would mean the opposite. Let's write the opposite. I should have made 2 sides to this. But at low temperatures, gases are not ideal. They don't act ideally. So that means at very low temperatures you cannot use the ideal gas law. But at high temperatures you can use the ideal gas law because the intermolecular forces are not going to make a difference. So now let's think about, well, what about the volume of molecules? I need a new page. So now we want to think about when would the volume of the molecules make such a difference, be so big compared to the overall size of the container that it would really affect how the molecules were behaving. So if you have low pressures, meaning that you have plenty of room for the molecules to move around, they're not crowded, so the pressure is relatively low. This is low pressures. At low pressures, there's plenty of room for the molecules to move around and bump into the size of the container. So at low pressures, the volume of your molecules, this is an O, volume of molecules, is irrelevant compared to the overall volume of the container. So I don't know if you can read that, but the volume of the molecules is irrelevant compared to the low volume of the container. I mean the overall volume of the container. So at low pressures, you can use the ideal gas law. Low pressures are ideal. But what happens when pressures increase? Let's say we push this piston all the way down. So now we have all these gas molecules in here, but the pressure is much greater, so they are really taking up the actual size of the molecules. The actual size of the molecules are taking up a lot of the room in the container. So when you had high pressures, the volume, the actual size of those molecules is a big percent of the overall volume. The actual size of the molecule starts to make a difference. It starts to affect, they're so close, they're so big that the intermolecular forces can then make a difference. So high pressures are not ideal, because if the molecules get to be so big relative to the overall volume, then they're closer together and they can start having an effect on each other. So high pressures are not ideal. At high pressures, you cannot use the ideal gas law. You can't. High pressures are not ideal. You can memorize this, but I prefer just to think about it. You know, well, what's happening at high temperatures? How fast at high temperatures are the molecules moving fast? If they're moving fast, they're not going to be able to attract each other. This is explained in your note packet. In your note packet, they give you this graph. So here, remember, if for the ideal gas law, PV equals nRT, if we say we have 1 mole of gas, then N would be 1. And so if we rewrote it as we manipulated it, when we have 1 mole of gas, your pressure times your volume over your R times T, that's going to be equal to 1. So that's what this line is here. This is representing at ideal gas, PV over RT will be 1, just a straight line. So here they've shown you gases and how they actually behave. So let's just look at the blue one, which is carbon dioxide. So at low pressures, well, actually, these are not low pressures because we're up here. So at low pressures, very low pressures would be close to 0, because this scale goes from 0 to 200 to 400. So right around here at very low pressures, everything is very close to 1. But once pressures start to get high, this would be about 75 atmospheres, which is huge, tremendous pressure, you're deviating substantially from an ideal gas. This graph shows you in terms of pressure, not in terms of temperature. So you can see, and you just have the scale here is kind of funny because low pressures would be very close to the y-axis, because low pressures would be like 1 atmosphere, 2 atmospheres, and here you're going from 0 to 200 in this small space. So once you move away from the y-axis, things start to deviate. Carbon dioxide is you have 12 plus 32, 44 grams. It's a pretty large molecule, so it deviates more. Where do we have hydrogen is the red line, so it doesn't deviate as much at the beginning, but eventually it does. And I think that's where we're going to end.